All right. I think I'm coming through. Okay. So thank you for introducing me. This here is talking about AllJoyn. It's a kind of a software framework that is used for the Internet of Things. It's kind of up-and-coming technology. Also a little bit of a protocol, but it's more of a software framework. So first of all, AllJoyn 14.06. Paul and I were talking about this earlier, a couple minutes ago. 14.06 is just the version number. It's 2014, June of 2014. That's the versioning scheme. It's actually just only the second release of the software. And so it's pretty new software, and it's still up and coming, still developing very rapidly. Very exciting technology. So I'm a software engineer with telemetry. We provide IoT infrastructure and services. We do work with AllJoyn, but that's not really our core competency. We just thought it'd be a pretty fun thing to talk about, up-and-coming technology. So before we get started, I do have a few links. If you go to the top link, I see some people have laptops. Feel free just to open up your laptop and maybe go to one of these links. So the top one is the examples that I'm working through. These are the AllJoyn examples that ship with the AllJoyn latest release of AllJoyn. These are only the Android examples. There's also iPhone examples, regular Java examples, some C and C++, Objective-C examples. I just chose Android because I'm a little bit more familiar with Java and Java technologies. I find it a little bit easier to read. The second one is actually the source code for AllJoyn. And it's C++, but it's actually surprisingly easy to read C++, so don't be scared. If you want to go browse through it, some of the comments are interesting. And lastly, here is the link to my slides. I do have some links throughout the slides, so feel free to look at those if you have a chance. So there's some interesting links throughout those.
There's a typo presumably on Kellogg.
Yeah, so long story short, but when I was trying to come up with a Twitter handle, I couldn't use my last name because someone had already taken it, so I had to misspell it. So IoT is pretty much just embedded software. It's more like embedded software with extra security vulnerabilities, really, if you think about it. You take embedded software, embedded devices, and you just add interconnections between them, and that just opens up more security vulnerabilities. So it's a pretty big topic. It does add a lot of value to our lives, or it has the potential to, but it also has the potential to add a lot of security, disasters to our lives. So just gonna kind of walk into this a little bit. So there's a Mitsubishi in 2003. I mean, the Internet of Things, has been a keyword lately, but honestly, it's been around for decades. I mean, 2003 is actually not that long ago for embedded software. I know my dad is a software engineer. He's been doing it for 30 years. So in Mitsubishi in 2003, they had an incident where their cars, an attacker, if someone was deliberately trying to attack a car, they could disable the brake system by shooting large amounts of EMI radiation at the car. So I mean, you're talking about like 1,000 to 10,000 times the legal limit allowed in the United States, but still, I mean, you can still get a hold of that sort of equipment. So what happened in this particular case is there's sensors in the car that are detecting if the brakes were locked up, and to detect if the brakes were locked up, they would read low-level amounts of EMI radiation. And so if there's EMI radiation coming off the brakes, they assumed it was locked up, so they would release the brakes, because that's a safety feature, right? You got to make sure your brakes don't lock up and you accidentally crash the car or something. Well, it turns out if someone is intentionally trying to screw with this stuff, you just shoot a lot of EMI radiation, and voila, you've disabled the brakes, and now they're running through a red light into a semi-truck or something. That's a pretty big deal. And the interesting thing about this is, so we have laws to protect safety things, but all this was within required limits of the law. So even though you're living up to what the law says you should do, doesn't mean that's necessarily enough. I think they've tightened down the laws around this particular case in the last 10 years, but still, that sort of thing happens. And so as engineers, we have to be thinking more about the bigger picture. Another little disaster, slammer worm, also in 2003. There was a nuclear power plant. The safety telemetry data that was coming to the engineers and technicians, all that data was just became unavailable for 5 hours straight. This is more of a black hat hacker that did this. The last one was more of a white hat hacker, someone who was benevolent, trying to find security holes before the bad people found. This is actually more of a bad case. In this case, when they were doing an investigation for how this happened, the authorities found out that the nuclear power plant, of course, the engineers and technicians didn't actually like going to a nuclear power plant every day for work because apparently it's not really a fun place to work. So you tend to find a more fun office, maybe in downtown San Francisco or something. I don't know where this was, but somewhere more fun to work. So they would take the data coming out of the power plant and telemetry data, send all the safety information about pressure and temperature and radiation levels, and I don't know, I'm not really a nuclear physicist, what all you'd look at. But basically just safety information to figure out the health of the reactor and making sure it's operating correctly. So all this data was actually being sent across the internet completely unprotected. No encryption, nothing like that. It was just all being sent directly across. And this is a quote, this in the middle bullet point is a quote from someone who for some reason didn't want to be identified. Saying that basically the business value of having this telemetry data being sent across the internet to a different location, that they weren't actually sad about doing the way they did it because the business value they got from getting that information, being able to react to customers quickly in a really competitive world of the energy business, that was totally worthwhile, and they would probably do it again unless the laws prohibited it. So interestingly, this kind of a fiasco, I mean, a nuclear power plant, just being totally hacked into, was caused by an instance of unpatched SQL Server. The SQL Server instance had a vulnerability that had been known about for 18 months, and there have been patches for it from Microsoft available to download. All you have to do is click download and install security patches. Those patches were also available for 18 months, and they weren't installed because sometimes we have better things to do, like manage a nuclear power plant or whatever. And so unpatched software, so this hacker was able to find one small vulnerability in the whole system and go in. So this is normally the problems we see in regular IT systems. And this is also more of an embedded embedded system. I mean, I know nuclear power plants aren't normally what you think about when you think about embedded systems, but it is. There's also Internet of Things is a pretty common architecture of sending telemetry data across the internet. And to think that the vulnerability here in this case was just some old technology that just wasn't being maintained like we know it should be, it's no big surprise. So instead of high-tech security holes, it's just the low-tech things we've known about for years. It's nothing really interesting. If you've ever known, have you ever heard of Bruce Schneier? He's a really well-known security analyst. I personally like him because while he really does know a lot about the in-depth about like the encryption algorithms and which algorithm is better than another one and elliptic curve cryptography and all that stuff. He knows about that stuff, but he doesn't really talk about it. He tends to talk about the really basic level things. And so he wrote this blog, and if you have a link to if you've already downloaded the SlideShare, I'd highly recommend you go read this essay that he wrote. Yeah, you probably read it. It sounds it sounds like there should be like something really new, breaking news, but it's not at all. He talks entirely about Wi-Fi routers that you put in your home or in a coffee shop or at work. They did a study, and they did a study of like 15 Wi-Fi routers, something like that, and something like 13 out of the 15 had really basic vulnerabilities. Like most of them have they run some basic version of Linux, and off the shelf these basic these Wi-Fi routers had like 5-year-old versions of Linux that didn't have the latest security patches. Not even the latest security patches. They didn't have the security patches from 3, 4, 5 years ago. So these really well-known security vulnerabilities are widely available in the Wi-Fi routers. And if you think about it, a router is probably one of the most security critical pieces of a network. So if you can infiltrate a router, you can pretty much infiltrate every other secure part of the network. You know? It's pretty crazy to think that they're so wide open. So he took this concept of, okay, we have Wi-Fi routers that have all these such basic vulnerabilities, and now we're talking about making everything connect to the internet. We're talking about putting a refrigerator in a stove, something at a stove that something can like overheat and melt things down, or doors in your locks in your doors, or light bulbs in your office that talking about putting all this other embedded software up, and we can't even take care of some of the basic things we do already. So it's kind of a really big step back, and let's not think about, like, maybe we don't need to think about all the really high-tech solutions. Maybe we just need to take care of the really basic things we've known about for a long time. So a really big kind of eye-catcher there. And this is kind of my last one. So the University of Washington in 2010 did a study. So a bunch of grad students got together, and they wrote a paper. If you want to read the paper, it's also linked right there. It's a really interesting read. They took a car from that year, so 2010, it's probably made in 2009 or something like that. But a current car, they didn't name the manufacturer, the make and model, because for security reasons. And they just kind of poked holes in it, see if we do this, can we break into this? What kind of things can we do? If we hack into this piece, how much more can we get access to? And so this is straight from the abstract of the paper. So we demonstrate that an attacker who is able to infiltrate virtually any electronic control unit, so any electric piece of the car, basically, any CPU or MCU, can leverage this ability to completely circumvent a broad array of safety critical systems. So this translate a little bit. That means like you could, if you can crack into, say, the radio, you might be able to disable the brakes or something like that, and that's kind of a big deal. Again, just to kind of reframe this a little bit, cars these days usually have a lot of computers in them. Like, so your laptop, it's a computer, right? But car tends to have at least 10 computers, more like 100 computers, and probably these days it's closer to 1,000, and probably Teslas, who knows? But there's a lot of different computers. But even though you, yourself, or your team, or your company makes every single part of this car, and they know how it was made, and it interoperates in your tests, doesn't mean you can actually trust the parts you made. So an attacker can infiltrate one piece that doesn't seem like it's a critical piece, and affect the other pieces because they all trust each other. You can't assume trust. That's the big point I want to drive home, is that you can't assume trust.
So if they hack the brakes, they can change the preset stations on the radio?
Yeah, if they hack the brakes, they can change the preset radio. Right, so this is kind of a pet peeve of mine, is people who reinvent the wheel, and when it's done with security algorithms, it's really big disaster. And there's a few other things like distributed systems, consensus algorithms, and they're really complicated topics that people take for granted how complex they are, and then they try to redo them themselves. I remember previous job, it's not quite the same example, but previous job I had a well-respected engineer who wrote his own HTTP server for the company, and I was just like, there's so many other really good HTTP servers out there that have gotten all the security holes taken care of, they've gotten all the performance problems taken care of, they've gotten all the extensibility problems taken care of, and it's really well architected. And I looked at his and it's like, sure, yeah, it's really fast, you're right, it's really fast, but there's all these other gaping problems with it. Why don't you just use one that's already made and it's been around for 20 years? And so it's the same sort of thing. And again, AllJoyn is not just a protocol. AllJoyn is a software system. You can put it on a device and it works, and you're not reinventing the wheel. You don't have to look at a spec and risk implementing it incorrectly. It's an actual implementation that you can put in place and it works, and it takes care of a lot of the problems. So AllJoyn. So AllJoyn, again, is a piece of software. It's open source. I'm not clear on the software license. I was reading through it and it looked kind of like a BSD or MIT license, but you know how those licenses are. They don't really say what they are. They just kind of give you a short license. But so it's driven right now by the AllScene Alliance. So the AllScene Alliance just is actually a subdivision of the Linux Foundation. And they're kind of out there to provide marketing. But they also put together this whole logo board of companies that are participants. And this is actually a really small subset of all the partners. So some of the big ones, so Qualcomm is the original one. Qualcomm, the original developer of AllJoyn was a Qualcomm employee. And still to this day, a lot of the AllJoyn development is done by Qualcomm. There's also a lot of partners that aren't on this board. And there's even a lot of partners that aren't partners, or there's a lot of contributors to the actual AllJoyn code base that aren't even partners at all. So just because someone's not a partner doesn't mean they're not crucial to the ecosystem. So a big thing about AllJoyn is we have some really important logos here, like Sharp and Panasonic and LG. Those are some of the hardware manufacturers. So AllJoyn is targeting appliances. So Sharp makes TVs, and LG I know makes like refrigerators, and probably they need to get Whirlpool on there and make some washing machines so you can be notified when a minute your laundry's done. Or maybe better yet, actually transfers it itself. That'd be cool. And Symantec, that's another good one. And of course, the most important would be telemetry, right? My own company. So anyway, the point of AllJoyn is it makes communication really easy. So it's a communication protocol, but it's kind of a marketplace for functionality. So you have vendors like a TV might be able to have the functionality of offering up notifications. So a TV, 40-inch TV, can put a little toaster notification up in the corner that says your laundry is done, or the doorbell rang, instead of actually ringing, it just pops up on the TV because we all just sit on the couch and watch TV. So it does this by just offering up to say I have this ability to display notifications, and then another device in the home, like your washing machine that has no user interface aside from a couple old school buttons, can take advantage of that ability and just notify user via the TV or via a mobile phone, like a smartphone, or a tablet, like an iPad. So it's really cool distributed communication mechanism where addresses don't really matter and you just communicate fluently. So moving on to the next slide. When I started learning about AllJoyn, I thought about Ruby on Rails. I'm just going to take a minute to explain why I make that connection. So if you think about like 15, maybe 20 years ago, back when people actually referred to things as the World Wide Web is actually a thing we talked about. Back then, there was those technologies like Perl CGI scripts and PHP, classic ASP. Back in the days when we were just figuring out how to mix business logic with, say, HTML code, and we weren't even thinking about databases and SQL injection. If you know what SQL injection is, like Bobby drop tables, that was prevalent. Like almost nobody actually did databases correctly. There's so many websites out there that had insecure data. And all your online banking was wide open to crazy amounts of security vulnerabilities. Back then, remember that, there was all these problems that people didn't know about because they knew how to do one thing well. They knew how to make a website, but they didn't know all the corner cases. They didn't know how to do security well. They didn't know how to do HTTP caching well. They didn't know how to do all these other things that need to be done when you make a web app. But I mean, it's the problem of the web. There's so many different things you had to be an expert in to do it well. That we needed something like Rails. Like when Rails came around in 2004, I'm not really a Ruby developer, but I've learned a little bit about Ruby on Rails, and I was really impressed when I learned it because it provides everything you need. It basically just puts the developer on one small directed path, and you just, as long as you follow this small path and walk down this path and do what everyone else does, we're going to provide all these things for you. You don't have to worry about interfacing with your database correctly. Those huge, like 300-column SQL tables that don't really happen anymore because we provide you an ORM, and it gives you that object relational mapping for you. It also provides the ability to mix logic in with your HTML and do the HTML templating. And it does all that stuff for you, HTTP caching and all that stuff. All the things that were hard to do because you had to be an expert in all these broad array of things, it just brought it all in and made you, all you had to do was just be pretty good with this one framework. And so you started seeing things like hacker schools popping up in Silicon Valley and New York that would advertise that they could take someone who maybe got a college degree in English, or maybe no college degree at all, just someone straight out of high school. They'd bring them into this hacker school, and they would teach them how to program and program in Rails or some other framework like this. And not just program, but also get up and actually produce something that's good enough to start a business on. And they would do this in like 4 weeks, 8 weeks, somewhere really short term. And obviously these people aren't great programmers. They've only been programming for like a few weeks, right? But yet they can make something that's actually pretty good. Sure, it's not the best in the world, right? So you're not gonna, Twitter doesn't run on Ruby on Rails anymore, but it did in the beginning, right? And so this concept of giving you a large framework of things that you already do everything, a framework that helps you do everything pretty well, maybe not the best, but help you do it pretty well, is actually a really powerful concept. I see AllJoyn doing this. So the things on the left here, AllJoyn provides all these things. They provide software updates, and it provides some concept of security and identity. And they provide what's the core thing is communicating with other devices, which is actually pretty hard to do without AllJoyn. Relatively. It also provides discovery, which is part of the communication piece. With AllJoyn, discovery and communication are like just hand in hand. You don't even think about them differently. AllJoyn also provides something for media streaming, for audio and video streaming. So your washing machine can stream ringtones to your phone or something like that. It also provides concept of user interfaces, which I think user interfaces is where it really excels at. Because if you think about all the embedded devices you've had to deal with, embedded engineers are really terrible at doing user interfaces. Think about like your the thermostats, right? Thermostat on your wall. Every thermostat I've seen is terrible. Even Nest isn't really all that great of a user interface. It's just not bad, and so it stands out so much that everyone wants to use it. So with AllJoyn, instead of having all these embedded devices make their own user interfaces, they just offer up the information that they need from a user interface in the form of an AllJoyn interface, and let someone who's actually good at making user interfaces do it. So maybe a washing machine, if you have a lot of things to configure, I don't know what you have to configure on a washing machine, but say you had a lot of things to configure on a washing machine, you can offer that up to, say, your mobile phone or a tablet or a TV if you really love using a TV remote or a laptop, and use those devices that are good at doing user interfaces, configure the things you need for your washing machine or your microwave, or maybe letting the microwave ping your laptop to get access to an NTP server to set the time. Something like that, just basic things, just leveraging other devices on the network to do those things for you instead of doing them yourself. So let's embedded devices focus on one thing and doing one thing really, really well instead of having to do everything, doing a crappy job of everything. So the basic concept here is a distributed bus. So it looks kind of like this. This is one way to look at it. A little sneak peek on the next slide. This is another way to look at a distributed bus, or a bus. This is kind of more the traditional diagram of a bus. This is probably more what it looks like in AllJoyn. It's distributed. Most of the nodes in the network that you're going to probably be making are going to be these big nodes. I just call them like the normal AllJoyn nodes, like a thick client, I guess. And all thick clients are going to also act as routing nodes. This diagram is a little bit wrong because they only have one line between each of the regular thick clients. In reality, they're going to be mostly completely interconnected. But all thick clients act as routing nodes for all other nodes if they need to be. The thin clients would be the small clients on the outside, the light blue, smaller circles. Those tend to be very small single-purpose devices like maybe a connected light bulb or a connected light switch or sensor or a small single-purpose actuator, something like that you want to connect to other devices for some reason, and send information or leverage some functionality elsewhere. But those are the main difference between the thin client and thick client. For the most part, they're exactly the same, identical. It's a different code base, though. Thick client is made for easy programming, and the thin client is made for lightweight environments. So the thin client is written in really lightweight C. It's kind of hard to read because you do a lot of that bit shifting and whatnot. And also, probably the biggest difference is the thin client does not act as a routing node ever. But other than that, there's no difference. And the thin client you can run in like 40K of memory. So one of the, just stop right here, one of the biggest differences between, say, IoT and the regular internet. So the Internet of Things, or IoE, Internet of Everything, Internet of Devices, and the Internet of laptops and desktops and huge servers that sit in Amazon, is that laptops, desktops, and servers that sit in Amazon are relatively very powerful versus some of the devices that are going to be connected to the Internet of Things are going to be rather small, lightweight, like light switches or little sensors with a temperature sensor on it or something like that. It could be relatively lightweight. So you have to change the way you approach some of these things. A lot of encryption algorithms don't actually work that well if you don't have a huge, powerful server sitting behind them. We'll talk about that a little bit later. The other significant thing about this diagram is, in AllJoyn in general, is AllJoyn can span multiple transports. So by that I mean you could have an AllJoyn node sitting on top of TCP/IP or UDP. You could also have it sitting on top of just raw Ethernet Wi-Fi packets, 802.11 ABGN packets. You can also have it sitting on top of Bluetooth. You could have a Bluetooth node talking to a Wi-Fi node that's like 2 or 3 hops away. So you can actually span multiple different kinds of networks. I don't know if I mentioned it, but I know Paul mentioned earlier Thread. There's that Thread technology that was announced earlier this week, or the Thread group. It's a new wireless technology. It looks pretty promising. I'm actually really excited to see how it pans out. But they're already a partner with the All-Scene Alliance, and so you'll very soon see Thread support in AllJoyn, probably the next release, I'm assuming. So that'd be just another thing you could span. You could have a node sitting on Bluetooth connected to your phone, which connects to your refrigerator, which connects to Thread and a sensor way over there. And you could have a whole bunch of hops going through trying to route one message to another. So that's a really cool aspect. So just because things aren't on the same transport doesn't mean they can't communicate. So this really, if you're seeing this, it really simplifies the communication aspect.
So in a sense then, AllJoyn somewhat mitigates the fact we have too many transport protocols?
Yeah. It's the one transport to rule them all. So yeah, it doesn't try to be another transport. It just combines them. Also, something to mention is AllJoyn is actually Dbus. If you know Dbus from Linux, AllJoyn is literally just Dbus. I think it's a new implementation altogether, but it's the same exact thing. If you want to know more like specifics about AllJoyn, most of the time you can just look up Dbus, and a lot of times they change like some of those C prefixes like Dbus _ whatever. They just changed to AllJoyn _ whatever. But pretty much it's the same thing. Same protocol. Just read the documentation on GNOME. So I think this is probably clear at this point. But so in this diagram, you have the two boxes. The big boxes represent separate physical devices. However, that's not actually important. So each of these hexagons are different apps that might run on your smartphone or app that runs on a Linux box, maybe like your TV or something like that. The app is what's important, and messages get routed between apps. And it really doesn't matter if it's on the same device or another device. a message, when you're programming an app, communicating from colon 1.1 to colon 1.6 is the same procedure as programming from 1.1 to 1.5 or 1.1 or 1.2. It's all the same procedure. It looks identical. So communication aspect is absolutely just a breeze. It's so easy. All right, so we're going to talk about security aspect of this. So does anybody have any questions at this point? You can ask questions whenever you want. I think the most important point at this point is you understand that these are just interfaces, and it's like a kind of a marketplace where you just offer up an interface. So.
Is it a publish and subscribe kind of interface, or is it a publish subscribe interface, or just a publish and result?
It's a RPC interface. So it's really similar to HTTP, except for there's no addresses. So
one device can call, constrained device can call only to one call.
I think there actually is multicast support, but I'm not clear. Well, no, there is, because when you come on for discovery, there's multicast support, right? So when a device comes online, it's going to do a multicast or a broadcast to see if there's other devices on the network that it can use, other functionality. So there is some multicast, but in general, when you're consuming a service, generally you want to go to a single point. I think even beyond discovery, I think there actually is multicast support. So yeah, I think there is full multicast support. It just changes some of the semantics. It's like you don't usually get a response when you multicast. So some of the semantics are different, but yeah.
But is it only one way? The device can call the router, or the router can instruct the device to do something. RPC is only one way. RPC, the client calls the server.
Right. Yeah. RPC.
The server cannot call the client.
Yeah. RPC. Yeah. Usually RPC. Yeah. Client calls the server and then returns a response, like you said. With multicast, yeah. I think AllJoyn does have some support. Probably full support, but you just don't often do it. Where you just broadcast out a value, like, oh, look, I just did this, like kind of like Facebook, right? Just broadcast out. So yeah, it does have that support, but I think generally RPC is a little bit easier for people to grasp, and so I sense that's more the direction where things are going to go. You're going to see a lot of interfaces that support multicast, or even streaming for that matter. AllJoyn does have support for streaming too, pretty low overhead. But yeah, so it does support multicast, does support mainly RPC, but also has support for streaming too. So streaming would also, aside from streaming audio and video, streaming could also be good for like telemetry data or something like that. So, but anyway, yeah, so it has support for a lot of different things. Again, it's Dbus under the surface, so if you have a specific question, if Dbus supports it, guarantee you AllJoyn supports it too. So I don't necessarily know all the stuff, but I have a general idea. Also, just a disclaimer on this from here on out, I'm not really a security expert. I'm kind of a back-end web developer, so I understand a little bit about security and have a general understanding, but don't take anything I say for gospel truth. I probably will say something wrong. Right. So these are, actually, I'm going to go to open up a web browser for a second. Right, so I linked to this earlier. This is just the samples, the Android samples are taken directly out of the AllJoyn repository. But I'm going to jump real quick. Slightly different might be. So if you are browsing through, if you're on your laptop, which I totally encourage you to just crack it open and just kind of walk through some of this. This is pretty much how all the examples are laid out. So there's that secure folder. There's several folders underneath the root level. The secure one is the one I'm most interested in because we're talking about security and identity here. And then underneath that, there's several other folders. Service is the service side, and then all the other ones are just clients that connect in various ways. And then like normal Java code, you have like 16 directories nested in each other for all the different. But anyway, so just to go through this real quick, in order to make an AllJoyn interface, you make a normal, if you're in Java, you make a Java interface. If you're in Objective-C, I think there's like protocols or interface. I don't know what they call it. I don't actually know Objective-C. But you annotate it, in Java, you annotate it with this bus interface marker. Annotation is just a marker. And you give it a unique name. And then to make a method, you do this bus method. And that's all. So it's pretty easy to do AllJoyn just to offer up new functionality. To make it secure, you just throw on the secure attribute. And then from here on out, security and identity is seamless and invisible to the developer for the most part. At the 14.06, the current release, it's actually not as seamless and invisible as we'd like, but I think it probably could be. Yeah, it doesn't say it in the comment here. There's another thing I'm going to show you in a bit. There's more code involved to do it. But honestly, it could be as simple as just doing this.
So that suggests that every interaction gets the same level of security, right? The same
Yeah.
assurance.
Now, there's another thing you have to do to specify all the different ones. And that slide I just had up with a bunch of jargon on it, that's actually, we're going to basically spend the rest of the time talking about each method. But for the most part, security and identity is just totally seamless and invisible to the developer. I think this is a good thing because it puts you on that guided path, those rails, to just do the right thing and do things generally well. Maybe not perfect, you might have some problems in it, but it's generally well. So I think this is a good thing. So again, all these examples throughout this entire repository, they're nested really deeply, but it all comes down to two files. So basically don't veer out of the source directory, just stick straight to the source directory and don't look at all the other Android nastiness. And so we already went through the secure interface, that secure interface.java. That's just Java interface. And then this service.java, I think they're all called service.java, is just the actual code that you need. Wait. This is not my computer. So this is the other side that you need to do in order. So we put the secure attribute on the interface, and then when we actually go in and create the client, this is kind of part of the main method. I mean, it's Android, so it's a little more complex, more event-based. But this is essentially just the main method. You create a bus attachment, which is like the distributed bus, like the kind of the daemon that listens and routes traffic. And you have so you just register auth mechanisms and register your auth listener. So your auth listener implements and watches for all the different auth mechanisms and methods that we use. So okay, so here is one of the auth listeners. So again, Java class auth listeners implements auth listener, and it really just has two methods. So actually, again, there's the slide I just had up had all these auth methods on them. We're going to talk a little more about what they mean, but this particular one is the service, so it actually has to implement all of them, and the clients only implement one of them. So we're going to talk about this in a second. Actually, I think we're going to talk about them right now. I think we're done looking at code. We're back. Right, so this slide. So here's all the auth listeners. These are actually not all the auth listeners. These are just all the interesting auth listeners. So we're going to talk about each of them individually, but these are just codes they're actually strings. So you can do like space-separated strings of all the auth listeners that you support. Right. So just to talk about so AllJoyn RSA. So RSA. First of all, RSA is a slightly different story because so RSA it's got the encryption and it's also got the certificate, and it's also got this key exchange. It's a pretty large, encompassing protocol that encompasses a lot of different aspects. So asymmetric keys and certificates, and you also need some sort of trusted CA or certificate authority. Now, you don't always need it. You can always just self-cert, make your own certificates, but generally you need some sort of trust. If you don't have a certificate that's authorized or issued by a trusted entity like a CA, then it's kind of meaningless because anybody can make it. So that's kind of a problem with it. However, it's generally pretty good. And on the internet, this is like nobody even questions. You just always use RSA because it's just so versatile and it's good for everything. What we see with IoT is there's actually, because of the way IoT changes the landscape, since you're working on smaller, lighter devices, and you also have a lot of large cardinalities of devices out in the field, RSA looks a little bit less attractive, and some of the what used to be less attractive options actually become more attractive. So AllJoyn SRP KeyX or key exchange, AllJoyn SRP logon. These are two methods that are pretty similar. So they both use something called threshold cryptography. So I've been working on a book. I had to read a little bit about threshold cryptography. It's a pretty interesting study where you can create public and private keys without actually requiring trust from any other entity. You don't need a CA. You can just leverage a few different participants in the system and create trust out of thin air almost without trusting anybody else. It's a pretty cool little thing. So aside from threshold cryptography, the main key thing is, so the logon is username and password. And of course, I think we probably understand that there's some problems with the username and passwords. First of all, when you're talking about machines, the key point with passwords, the key value is that a human could just memorize a password and never write it down, and no one could break into their head, right? Well, theoretically. But that doesn't really apply to machines. They have to store it somewhere. So passwords kind of become less attractive. KeyX is a pin-based solution. So it looks something more like this. If you ever paired your phone with your car or something like that, usually it'll bring up a 6-digit PIN number. With AllJoyn, it's a 6-digit PIN number that pops up on your car, and you type it in on your phone, and so some sort of identity is established. It's not really the strong form of identity, but it is some form of identity. You're establishing that whoever is doing this is in control of both devices, the car and the phone, and they are in the car, and they had access to get into the car. So you're establishing some level of trust. So it's kind of a weak form of identity, but it's actually worthwhile. And I think with IoT, this is probably a very legitimate form of identity that's probably going to be used quite a bit. I don't think, most of the time, you probably don't need to know that the user is Tim Kellogg and his social security number is 123456. And you probably don't need to know all that stuff about the user just to be able to use the device. This is probably good enough for a lot of cases. The last little piece here, okay, so ECDHE. This gets a little crazy, like cryptographic stuff. So elliptic curve cryptography is pretty intense math, at least to me anyway. I think if you're a mathematician, you'd be like, oh, it's really simple, but to me, it's pretty intense. But what you need to know about that is it's a relatively recent advancement that's pretty good cryptography. And then DHE, Diffie-Hellman key exchange, is actually an old key exchange that's still used in TLS, and most of the time people use RSA instead on the open internet. But again, some of the reasons why people liked RSA over DHE actually kind of fall away when it comes to IoT. So for IoT, you have lighter devices, and DHE, it's a lot easier to generate a certificate. I'm gonna forget what all the other things I was supposed to say here. Oh, right, the other thing is RSA. When the certificates are generated and validated, RSA, you only validate one side of it. So like if you're a web server, you're only validating the clients who they, or actually the client is validating who the server is who they say they are. With DHE, it's actually a bidirectional, and you validate both sides of the connection. When we're talking about IoT, IoT is fully distributed, and so this sort of thing is actually really useful where you validate both sides, and no one entity is more reliable than the other. I'm gonna speed through this. We've already talked about ECDHE. This is one subset. So we've already established that ECDHE has some sort of identity. But aside from the certificate validation, there's no verification of identity. But it still has a strong form of encryption. And this is actually probably good enough for a lot of cases. Maybe not all, but definitely is valid. And then we also have PSK, so pre-shared key. If you've ever logged on to a Linux server via SSH or push code to GitHub or something like that, you've probably used pre-shared keys. It's just where you have an asymmetric key, and you share the public key with the trusted person, and when you log on, it automatically knows who you are because you used the encryption key to talk to them. And you can also use a password, although we've already talked about how passwords are not really a great idea. So it may not be a great idea to use a password, but that could be an appeal. And then lastly, it also has support for DSA. I don't know a whole lot about DSA, but it adds a little more functionality there. All right. So anyway, ending right now. So here's an XKCD comic. It's kind of a fun one. Basically, just kind of go back to the beginning. We have all these really complex ways, like elliptic curve cryptography, to deal with encryption and identity and security and connections. But in reality, a lot of the stuff we just don't look at the small things that don't apply. That apply, like back to like the nuclear power plant example. They might have actually probably didn't do anything. That's probably not an example. I don't know, Wi-Fi routers, how about that? Where they might have taken care of all the cryptography, making sure that the communications are secure, and they didn't patch the software. Just really basic things. So you might be the engineer, and you might be really loving the 4096-bit encryption and dealing with all these cool algorithms, but in reality, you're missing all the wide open gaping holes. And so just to bring it back, reinventing the wheel isn't a good idea, so AllJoyn I think is a really good piece of software. So you can use something that's already created. Some people have already evaluated it and decided that it's solid. But that's pretty much all I have for you. I have Twitter if you want to follow it. I do. So I mentioned earlier there's a book in progress. It's kind of behind schedule. Should have been released by now, but we're getting there. But any of that, we have a little more time for questions, I think. So if anybody has anything.
Question? Is it practically used anywhere in the industry? I mean, anybody is building products and services based upon, you have shown some LG and all these things.
Right. So they're on a 3-month release cycle, and they have 2 releases. So it's pretty new technology. I'm on the mailing list, and I watch things coming in, and it's super exciting watching new technologies come in. And the involvement level is just spiking tremendously. You have, I think just this past week or two, they had 8 new partners. So there's a lot of people that say, yeah, we're going to use this. We're going to bank our next 10 years of our business on it. But it's still at that new state where people aren't quite actually using it. I mean, there are a few devices out in the field that do have it. There's some devices, there's some appliances you can buy in the store that have support, but for the most part, there's not a lot of broad support for it yet. But that makes sense. It's only, not even a year old. So.
Does it work on both Bluetooth and IP technology, or it's just the communication is independent, right?
So if I understand correctly, the official support is Wi-Fi only. It used to be Bluetooth only. They did Bluetooth and Wi-Fi, and they realized there was problems with Bluetooth. So they're rewriting their Bluetooth support. Community supported, so theoretically, if you ask them, they'll say, oh, we support everything, because the community has support for a lot of different technologies. So ideally, you could connect over just about anything. Even like power line communication, you could theoretically handle this. Realistically, I would say Wi-Fi and maybe Bluetooth. And Thread, again, Thread is going to be, they're their partner already, so I expect to see the next release have support for them too.
For the authentication method, native types all can support. How is the requirement like derived to a work group particular for that? Are there work group more for subcommittee about basic service law? But the security across cutting in time committee, do you have a particular work group to define that, or how is it done in all thing?
I think organizationally.
Organizationally,
Does all seem to have,
you support electronic certificate, support using password or PIN, right? It's different mechanisms you need to support. Right? You support the SPKI. So how was this derived? Which one would be supported?
So it has support for all those methods I mentioned. There's no single identity that's pervasive across the whole entire system. So let's see. I don't know if there's a really great answer for that. I think the main thing I'd point out is that what makes sense for the regular internet with humans might not make as much sense for devices, because devices have kind of a loose.
Right. So what will do but for each device, what will be a private credential that may be widely accepted? Right. That's where this protocol is support, right? This is a token support. This is part of that. So there's a working group, or it's more.
is it noteworthy that the identity protocols in this community is mostly tracking and OAuth and Connect were missing from that list? Because
Oh, right.
certs and passwords are technologies that.
Right, those are old technologies. Yeah, okay, I get you. No, that makes sense. So one of the issues with OpenID and OAuth is that you have to connect to a third party. It's often out on the internet. And by connecting out into the internet, you open up your security surface attack area. Most of AllJoyn is concerned only with local networks. So it's going to only contact within your home, within your car, whatever, just a small area. And so by offering up like an OAuth authentication mechanism, you're actually opening up more security vulnerabilities by going to the open internet. And so I haven't seen any discussion at all about talking about OAuth or any of those mechanisms, just because of that fact that you'd have to buy a device that knows how to authenticate. And it's built to be a distributed system, built to have no single authority, no single point of failure.
So I think that's actually a perfect segue to our next speaker, because George will talk about scenarios, if I understand correctly, where, first of all, your authorization server that issues these tokens need to be on the internet. It could be in the home. So perhaps there's nothing incompatible there.
Okay, cool, excellent.